Good morning. I am Dr.S.J.Mohan, Professor, Department of Civil Engineering, Bharat Institute of Higher Education and Research. I am going to talk on the subject of structures on expansive soils. Under this subject name, the topic what I am going to cover is the soil stabilization methods. Soil stabilization methods means I should first tell what is soil. What is the stabilization methods? So both put together we should study to understand the soil structures on expansive soils. Soil stabilization method, if you want to define the soil, it is defined as the entire unconsolidated material that overlies and is distinguished from the bedrock. It's just a geological meaning. Composed of loosely bounded mineral grains of the various sizes and shapes, botanical. Contains voids of the very sizes. These voids contain air, water, organics, things like that, as a soil mechanics. If you look at the soil, some part is air, some part is water. And 50% will be mineral soils, and some part may be an organic material, which may be decaying also sometimes, discoloring, decaying, things like that. But air and water could not be isolated just like that, because they are mixed, all mixed between the molecules or very fine grains of the minerals. The air entrapped and water entrapped into this mixture, we call it as the soil. Then stabilization. Soil stabilization is a technique to refine and improve the engineering properties of the soil, such as mechanical strength, permeability, bearing capacity, or angle of internal friction, things like that. So, etc., mechanical characters. Soil stabilization is also defined as a chemical or a physical treatment which increases to maintain the stability of the soil to improve its engineering properties. So, stabilizing to improve the properties, and sometimes we use chemicals also, or some physical treatment also you give to improve the soil stabilization. Let us see what are they. There are different types of soil stabilizations: biological, physical, and chemical. Biological soil stabilization is achieved through afforestation or planting, and its main purpose is the erosion control. You know, when there is a forest area, that because of the roots of the vegetations hold the soil firmly so that the soil erosion can be avoided. And such type of the erosion avoiding is biological soil stabilization, because the roots and then green vegetations of the soil protect the soil from not for eroding it. That's one type of the stabilization of the soil. Soil stabilization aims at improving soil strength, increasing resistance to softening by water through bonding of the soil character together, waterproofing, particles, combination of two. Usually, the technology provides an alternative provision to structural solution to practical problems. What Sherwood 1993 identified was, when there is a moisture variations in the soil, then the compaction of the soil also changes. But there is an optimum moisture content at which the soil can be compacted and stabilization can be very best, it can be exploited. And that moisture content you may sometimes call as an optimum moisture content for the compactions. So that was the science of the soil moisture content and compactions. As far as the soil is concerned, gradation of the soil depends on the particle shapes. For example, well graded, that is uniformly the sizes are going to vary. So 10% of smallest one, 20% is next size, 30% is third size, 30% is the fourth size. Something like that, the percentage wise, they are all uniformly distributed. You call it as a well-graded soil. But uniformly graded soil it is not the distribution. A same size of the soil is distributed most of the places in the soil. One type of the micron size of the soil may be present, maybe 70 to 90% of the soil, they are called uniformly graded. Well graded, uniformly graded, and gap graded. Gap graded means there may be some larger sizes of the particle and there may be a very small size of the particle. In between sizes of the particle may be missing. Then they are called as a gap graded. Not only that soil, but it can be a bulky soil, an angular soil, subangular soil, and sub-rounded, rounded, and platy soils are also there. They are all the textures of the soil which are mixed along with a well-graded, uniformly graded, and gap-graded soils. That is as far as the soil is concerned. Then moisture. Most important factor affecting the engineering characteristics, the moisture, which affect the various greatly depends on the soil type. The moisture and soil types affect the engineering property substantially. The coarse-grained soils usually remain unchanged. Fine-grained soils are susceptible to shrinkage and swelling, and this shrinkage and swelling is because of the moisture content presence. And when there is a variation of the moisture content, the property of shrinking swelling will be enormously varying. That is because its compaction also varies. So when you come into the bearing capacity, the ability of the soil to support the load applied by the engineering structures. The soil with insufficient bearing capacity might fail by shear, allowing the structure to sink and shift or rotate or bend. Dense and well-graded soil with angular particles generally has good bearing capacities. Well-graded soil and angular particles has a good bearing capacity because well-graded means all particles are uniformly distributed in the soil. So the compaction you can attain very nicely and then very reliable level you can get it. Soil will fail because of the shear movement of the soil. When there is a loading on the soil, then the soil has to go away from the loading point and it bulges out. Because the stability on the top surface is not there for the soil, it bulges out and moves out, and the soil is scoops along with bulging of the soil. You call it as the failure of the soil. Or the surface of the failure is called the failure surface. And that can happen on one side or it can happen on the both sides of the footing. But failure can happen when there is a soil movement occurs. Effect of soil compaction. Settlement. The compaction brings a closer arrangement of the soil particle, which in turn reduces the settlement. Compaction means well compacted soil means more and more dense soil. You call it as a compacted soil. Shearing resistance increases the soil density, usually increasing the shearing resistance. When density is higher, its shearing resistance will be very high. Then water movement. Compaction decreases the soil and number of the void, leaving less room for the water. Water movement. Then volume changes, generally not of great concern except with clay soils. So sometimes because of the water fluctuations or the water content fluctuations, then the clay soil behavior will be different. Volume changes will be there. Shrinkage limit will exceed it. And compaction will be very less. All those things will affect the engineering property of the soil. So if you take a soil and if you go on vary the moisture content, then the dry unit will be go on varying. After some time, it fall down also. So when you just go on plot it, so when there is an hydration, then it goes on increases. After attaining the maximum dry unit weight, even though if you increases the moisture, then the compaction will be reducing it or swelling will be there. So the swelling means it will increase the volume and occupy the more moisture into it. That you call it as the swelling. Then the saturation it will increases because of the moisture content, or it will be almost like a quicksand, or it can be a submerged soil. So swell water begins when forcing the grains apart. So it is swelling. The adding the cohesive water will shrink sometime. So there is some moisture content where the dry density will be maximum. The maximum density attain the moisture content, you call it as the maximum compaction or optimum moisture content. That is an optimum moisture content where your dry density will be touching a maximum value, and that you call it as the maximum compaction. If you take different soil, a well-graded soil, silty, sand, silty, grade, this type of the curve, the variation of the moisture content with respect to dry density will have different hump curve. Then if you have the profile of these curves, you get the zero air voids curve also there. So for example, the curve phi, if you take, it's a uniform fine sand, will not have much hump in that. Well-graded clayey sand will have a very steep hump because when the moisture content is increases, then suddenly swelling will takes place. So these things are the behavior of the soil. From this behavior, you can find out what is the maximum compaction you can get from the soil. The maximum compaction means the maximum strength of the soil stability will be very high because of that. So for the stability purposes, the maximum compaction is needed. But stabilization can also be achieved from the external agencies like the geotextile materials, chemical stabilizations, mechanical stabilizations. Geotextile means there are some material you can make use of it to keep the soil intact or in conditions. For example, a geofabric. You introduce a geofabric, then you put the granular subbase on that. Then you pump it. Then the original subgrade will get compacted. Then if you pump it, and then if you go on vibrate and move it, then you get a very nicely compacted soil using the geofabrics. This you call the granular subbase and weak subbase. If you introduce a fabrics, then you get a better result of compacted soil because of the geotextiles. And the geotextiles have different shapes and varieties are available nowadays. So the sizes, the membrane sizes, the mesh sizes are all shown in my slides. Geogrids, geocomposites, geomembrane, geotextiles. So soil is stronger in compression than in tension. To improve the strength in tension, geosynthetic list in soil for soil reinforcements. Typically speaking, the tension capacity of soil is not at all there. There is no tension for the soil. But if there is a geogrid presence, then some amount of the shear tension it can take. That you call it as the improving tension, improving the tension strength of the soil. Our soils are being kept in position because of the geogrids when there is a separation happens in the soil. So the reinforced earth wall construction is one of the geosynthetic fabrics. You see some steel rods are being laid there over the soil. Then next layer of the soil is spread. Then again next layer of the steel layers will be there. Strips are there. Then these strips are connected between both the retaining structures on either end of the soil. When the soil is being connected by the both ends, when the steel strips are holding both ends of the side protected walls, then soil inside gets compaction and stability will be achieved 100%. So without having an embankment on either end, because of the geostructures which are steel strips, which can use as the uh, retaining structure, and your retaining wall and embankment part of the soil and occupation of the space are being avoided. So this you call it as the reinforced earthen wall, which is being under construction, is shown in this slide. Sometime nailing of the soil. You take some solid block or a steel block or a timber block. You have a hole in that. That hole, through the hole, you embed a steel rod into that. Then you pull the steel rod and jack it up and then lock it with a lock nut. Then that amount of post tension being applied on the bulkhead, that will apply a pressure on the soil to retain the soil. You call it as the soil nailing. The fundamental concept of soil nailing consists of reinforcing the ground by passive inclusion closely spaced to create in situ a coherent gravity structure and thereby to increase the overall shear strength of the in situ soil and restrain its displacements. That you call it as the soil nailing. It is predominantly used for the soil stabilization in case of the roadways or highways where you need the space for service corridor also. Then you may not have to, we may not have the embankment on either ends of the elevated corridors. Then you have to have the soil nailing. Chemical stabilization. Chemical stabilization is adding the granular or chemical admixture to the soil, used when an inadequate soil is too costly to remove and replace the common methods. Suppose soil is abundantly available and a very big area the soil spreads. Then you have to treat the soil by means of some chemicals to make use of the soil as a foundation material. The material what you use, the chemical stabilization, are the Portland cement, ordinary construction cement, or lime, fly ash, mixtures, or bituminous compound or bituminous cement. Most of the time, we use Portland cement because easily available, easy to handle, because lime you get very less quantities. So the Portland cement mostly used because fly ash is a component used in Portland cement also. So we are not much using the fly ash and mixtures. And bitumen is mostly used in the roadside. So bitumen scarcity is also there. So chemical stabilization, most of the time we use Portland cement. So graded well soil, soil well graded, gap soil, and other things. When soil gradation is there, accordingly the initial estimation of the cement by percentage by dry weight. You add 5%, 6% and varies up to 10%. Depending on the soil classification, you go on add the cement and vary the cement content to see that your stabilization is attained to a maximum value. And this you call it as the chemical stabilization. Under chemical stabilization, your mixture you can make use of it or bituminous. Lime and fly ash, lime, cement, fly ash, then expedient mix, 1% cement, 4% lime, 16% fly ash, 17% of soil, expedite mix, then bituminous mix, not normally available to the marine corps. Types include asphaltic cement, cutback asphalt, and asphalt emulsions. So these are all the material use it in the chemical stabilization, and sometimes the mixture of these admixtures are also used. We said Portland cement separately, lime separately, not necessarily. A combination of all those things are also possible for the chemical stabilization, as it is explained in this slide. Expedite the mix. For example, 1% cement, 4% lime, 16% fly ash in 79% of the soil to stabilize the soil. So this is another formula, just like a mixed design, what you do in concrete, you do a mixed design in the soil also to stabilize it. So when you do the chemical stabilization, obviously you have to do the drying of the soil. Short-term effect, reduce the moisture content level of the wet soil to improve its workability, keep protection on the schedule and extend construction seasons. So, as I said in the beginning, the moisture content is very important. Drying of a soil is very important when you want to go for the chemical stabilization. The optimum moisture content you reach it, then you go for the chemical stabilization, which is very important to have a sound soil as a sub-base. Then you take the chemicals in the tanks and then spill the chemicals. Soil enhancements, its effect, longer lasting than drying, but not permanent. Speed constructions with stable, weatherproof working platform, maximize use of the low-cost on-site material, reduces plasticity, improves the workability by some soil modification you can do, and change the characteristics of the soil as listed above now. So that you call it as the soil modification using the chemical stabilization. Soil stabilization is done. All soil modification benefits and permanently increases the compressive strength, increased load deformation properties, and improve the durability during freeze-thaw and wet-dry cycles to be incorporated into the structural designs. That means you have to improve the soil as a structural material. It forms a part of the structural composition in your structure. The soil is no more a soil. The stabilized soil is also a part of the structure in the whole structure. Because load deformation it reduces, strength, compressive strength increases, and freezing and thawing effect is minimized, and wet-dry cycles are minimized, and incorporated in the structural design by itself. So structural design, the soil effect is also accounted, the soil structure interaction, where the soil properties are very much involved in such cases of the such area of the studies. So a very big plant, a soil stabilization. This big plant, what you see in the figure, is a moving plant. One side you see a soil there, other side you see a bitumen road on the other side. So meanwhile, it does the soil stabilization by chemical stabilization. Quicklime, hydrated lime, lime slurry, and a suspension of quicklime formed by the exothermic reactions, and then it caused by the alkaline formed during the calcination of the limestone. All those things are being done in a single stroke in the single equipment. That full factory will move on the pavement so that you get the ready pavement on the other side. It moves on the soil, it conditions the soil, then it lay down the sub-base, then it lay down the overlying, then it lays down the soil fabrics or textile, geotextile fabrics. Then it also lays down the concrete base or the bituminous base was a pavement. So a single moving unit is now developed for soil stabilization and pavement constructions. Now we go to the mechanical stabilizations. There are different types of mechanical stabilization. Maybe we can see one by one. Preloading of the site or pre-compressions. When you have a poor soil, then you just load it with you dump some soil over that and leave it for some time. Then the dumped soil will compress the poor quality of soil and then gets compacted. Then it will reduce the consolidation settlement. Then the soil will be upgraded. So if you load a very big large area, your very big large area will be get compacted. So simply place a surcharge fill on the top of the soil that require consolidation. Once sufficient consolidation has taken place, the fill can be removed and construction takes place. So you remove those earth which is filled on that. Maybe a sand, if you fill it, then you remove the sand used for construction purposes. If you stack it with the bricks, or if you stack with the tiles, if you stack with the rocks, then you use all those things, build material for building the structure. Meanwhile, your soil also get compacted. Only time scale is the only required unknown factors here. The surcharge fields are typically 10 to 25 feet thick and generally produce a settlement of 1 to 3 feet. Most effective in clay soil. If you load it, then the clay soil get consolidated, then the settlement should be avoided very near to the 1/3 of the value of the virgin soil. The advantage is it requires only a conventional earth moving equipment. You just dump a soil. Any gradient contractors can perform the work. It doesn't require any skilled performing work. Low track record of the success. It has a very previous records of success. So most of the structures have been built on such type of the soil treatment. So they are all successfully performing their duties without any fail. So it is long track record of success is being achieved because of preloading. Disadvantage of pre-compression is the surcharge field must extend horizontally at least 10 meters beyond the perimeter of the planned construction. Your construction area is 15 meter by 15 meter, then it should spread 10 meters on either side. So 25 meters by 25 meters, you should preload the site, which may not be possible at confined site. A smaller site, it may not be possible, or some site is being occupied by the other agencies, confined site, it may not be possible. Transport of the large quantity of the soil is required. The surcharge must remain in the place for months or years, or thus delaying the construction. This is what I said in the beginning, the time scale sometime will be spoiling the construction activities, but time scale is required for the consolidation of the soil underlying when you do the preloading of the soil. Of course, this is a serious constraints on this, but pre-compression is one of the best solutions. Then vertical drains. You insert some drain pipes into the soil, then you put a pump and then drain out the soil. When the moisture content is gone removed, the soil gets contracted and then it settles down, and compaction you will automatically achieve it. The vertical drains are installed under the surcharge loading to accelerate the drain of improved soil to impervious soil and the speed of the consolidation. These drains provide the shorter path for the water to flow through the getaway from the soil. The time to drain the clay layers can be reduced from years to a couple of months. So you have to drain out the soil slowly because faster drain may not be possible. And this is a figure which shows how you can drain out the soil. You preload the site with an embankment, then you put the trial bores or something like a bore like boreholes where you put a sand there, then from the sand will evacuate the moisture. That evacuated moisture can be pumped out also. If your moisture contents are very high, you can pump out. Otherwise, you can leave with the moisture content in the sand. If you take out the sand, you get the wet sand by way of that removing the wetness in the clay soil, which is at the underlying level of your foundation. So water drainage patterns will be like an horizontal patterns will go to the vertical drains, and then vertical drains you can pump out the water. Then you get the piezometers, then you have a compression slow drains, soft and compression, the normal fill, sand drainage blanket, you remove the sand. Then you can remove the water from the sand also. From the figure is self-explanatory for the vertical drains. Wick drains are some small structures you can have it, then you can pump out the water so that a suctions can be created. The geosynthetics used as a substitute to sand columns. So geosubstitute you can insert it installed by being pushed or vibrated into the ground. Most are used at 100 meter wide and 5 millimeter thick. Just like an inspection gallery, you just construct it with the use of the maybe use of the geogrids or geosynthetic materials, then you pump out the water, then consolidation takes place at the lower level, which will cause us the compaction in the soil, and soil character will be improving or the stabilization wise. Typical insulation of the wick drains, as you see, there are 3 meters on the centers, then prefabricated drains you can put. Then there are alley drains, alubic, emeridrian, and coal burn drains, and Mebra drains. They are all the manufacturers, and they are being used in the site to drain out the water so that consolidation takes place and stability takes place in the underlying soil. In-situ densification. Most effective in sand, method used in conventional earthwork are only effective to about 2 meters below the surface. The in-situ method, like dynamic deep compactions of the soil deeper than, can be compacted from the surface. In-situ densification is you can at the site you densify the soil by you removing the soil and put the more compacted material into the soil so that, for example, driving a pile. If you drive a pile, it sends the soil on either side and soil get compacted. Just like that, it is used for the in-situ densification. You dynamically you give an impact, then the soil will be sent on either side. Away from that, then it causes the compaction in the soil. Then you put a vibrator and you go and vibrate it, the soil will be sent out on either end, then the other end soils will be compacted. The whatever the vibrator end you put it, you fill it again with the sand so that the soil fill up and compacted sand remain as a compaction. Long probe mounted into the vibratory pile driver compact the soil around the probe. Penetrates the space in the grid pattern similar to the vertical drains. Vibratory probe compactions are just as similar vibrators in concrete vibrators, but it is of slightly huge with high powered and then very high horsepower motors are being driven, and they are inserted into the loose ground where the soils are being sent on either side. Then you fill it with a stone or a soil so that the compacted soil will remain as compaction because of the vibration. So they are called the vibratory probe compaction. You insert this vibrator into the sandy soil, then the sand will be compacted on sides, then you fill that center part of it with a cement grout or maybe with a stone columns, anything you can make use of it. So this is a vibrator probe. You just insert this into that, then you fill it up with a compact material. So that's how you have the vibratory probe compactions is being achieved to improve the soil stabilization. But be careful when you transmit the ground vibration, the nearby structures also get vibrated. So foundation and structures interactions are being monitored continuously for the vibratory sources of the piles, vibratory piles. Sometimes if structure is very weak, which can cause us the cracks in the building also, because if it is a very brittle structures like mud wall construction or maybe a brick wall construction with a poor mortar, then the brittle failure can be induced because of the vibration generated by the vibrator Vibro-floats. So Vibro-flotation is a probe, includes the vibrator mechanism and water jets. Probe is lowered into the ground using a crane. Vibratory eccentric forces induces the densification and water jets, assist in the insertion and extraction. Vibratory probe compaction is effective in silty content in less than 12 to 15% and clay is less than 3%. Probe inserted into the grid patterns or spacing of 1.5 meter to 3 meter gaps. You mark it with the grid size and into the grid every node you just put a Vibro-flotation to compact the soil. So Vibro-flotation, if you think of the ground type and the relative effectiveness, sandy soil, it is very excellent. Silty sand, marginally too good. Then silt, it's poor. Silt, it cannot be vibrated. Clay soil, it may not be applicable. Then mines and spoils and good if angular. And dumped fill depends upon the nature of the fill. Garbage not applicable. Vibro-float cannot work. It move along with the vibrator and sets back. So it cannot compact. The vibrator cannot compact the garbages or vibrator cannot compact the clay soils. So vibro replacement stone columns. Vibro replacement extend the range of the soil that can be improved by vibratory techniques to include the cohesive soil and reinforcements of the soil with compacted granular column. And stone columns is accomplished by the top fed methods. So you fed with a stone, small stone granular stones, which will causes the compaction to remain in its own place. Vibro replacements and stone columns. So that's how the stone columns are being used. Bottom fed vibrator, adding stone. You can see the stones are being fed into the installation. Top feed Vibro-flotation. So when you put this Vibro-flotation, it sends out the soil outside. Then you dump with the stone columns. That's how the Vibro-flotation is worked, and that's how the soil stabilization also works. So dynamic compaction. Sometimes you can take a crane, you can use a crane, you lift a very heavy weight and hit it on the floor. Then floor will sink into the hard mud, which will cause us a compaction. If you go on seriously, if you do it, the full area gets compacted. Uses a special crane to lift 5 to 30 tons to a height of 40 to 100 feet. Then you drop this weight into the ground. The cost-effective method of densify the loose sand and silty soil up to 15 to 30 feet deep, it can densify it. Grouting. So you inject this special liquid slurry material into the soil so that the gaps in the soil gets filled with the cement grout, thereby consolidate the soil or compact the soil. Then you can use it for a better foundation purposes. Cementatious grout and chemical grouts both are possible. There are two types of grouts are available. And grouting method, you just send a probe inside it, then you send a pressure grouting and let it spread inside the soil. So intrusions grouting and permeation grouting. There are two types of grouting. They are self-explanatory. Grouting method, compaction grouting. When low slump compaction grout is injected into the granular soil, grouting bulbs are formed that displaces the densified and loosening the loose soil and the surrounding the loose soil. Used to repair the structure that have an excessive settlement. Yes. That's how the grouting machine is used for compact the soils. On grouting methods, you can bore a hole, then you can grout it. On the grout, you can have the structure straight away. Developed in Japan, they use a special pipe with horizontal jet that inject the grout into the ground at high pressure. The jet grouting is an erosion replacement system that creates an engineered in-situ cement product known as the soilcrete. Effective across the widest range of soil types and capable of being performed around the subsurface substructures and confined spaces. Jet grouting, valuable tools for soft stabilization, excavation, supporting the groundwater controls. So a very powerful method for grouting method for the stabilizing the soil. So stabilization of the soil, we have done extensive treatment and that should be understood well when you want to think of soil stabilization. Now, thank you for listening with me. Thanks for joining with me. So, thank for once and all. And I stop this lecture on this topic right now. Thank you. Thanks, one.